let's start chapter 4. Right, this is where the chapter 4 is titled the Dirac equation. Okay, and this comes up with the funny joke where Paul Dirac, that's his first name, was in a room with a. So Paul is actually an electrical engineer, I think, right? His degree is actually in WE. Correct me, Alex, if I'm not remembering this right, but he was in the room with a bunch of physicists. So he was, probably in the same room as, Wolfgang Pauli and all these famous physicists in quantum mechanics. And then, his joke is that I'm the only one who has the equation named after me in this room. Okay, so that's this joke. Okay, but we're going to see why we need the Dirac equation in order to describe the behaviors of electrons and photons. Okay, and this is what's going to lead us into this thing called the quantum electrodynamics, which is basically the quantum version of electricity and magnetism. Okay, and we're going to see why there's some shortcoming in the non-relativistic version of the Hamiltonian in the Schrodinger equation, right? That's why we have a dedicated entire week on quantum mechanics, or a week and a half on quantum mechanics. And we're going to develop a relativistic version of the Schrodinger equation with a little sidestep of this thing called the Klein-Gordon equation. Not very important to know about this, but eventually it'll develop into the Dirac equations, which is that allows Paul to make jokes in physics rooms. Okay, I'm going to have to learn all the math and on all the consequences to the solution to the Dirac equation, and things just get more complicated because what's going to happen is that instead of wave functions, these wave function turns into vectors of wave functions known as spinors, and we'll have to deal with the mathematical consequences of that, of keeping track of like all these indices within these spinors. And we're going to see that spin and angular momentum will naturally combine together to form a new conserved quantity. Okay, and we're going to see how we can, with the spin and angular momentum combined together, we're going to be introduced to these new quantities called helicity and handedness, and that's going to bring us to how to actually calculate the matrix elements for the Fermi-Golden rule. Remember, the whole goal of these two chapters is going to be calculating this MFI thing, and there's going to be some angular dependence in that. And that's because of this helicity and handedness that we're going to see from the Dirac equation. Okay, so useful thing to review for this chapter is the special relativity sections, right, in Thomson, and also in the quantum mechanics, right, the stuff we dove into a couple of weeks ago. Okay, so Griffith's chapter 7 is his version of this. The notation is a little bit different, and he doesn't use natural units and stuff like that. But if you find that the Griffiths version is actually a good additional side reading, right? Not side reading, a parallel reading to Thomson, feel free to utilize that. The process is very similar, but with the notation is just a little bit different between. Okay. All right. So to get started, right, in order to calculate this Lorentz invariant matrix thing, right, once again, this MFI thing that we have to always calculate in the Fermi-Golden rule, okay, what we need to do is actually associate these Lorentz invariant matrix to these things called Feynman diagrams. Remember Feynman diagrams? So let's say you have an electron coming in, right, they exchange a photon with another electron, for example, and then they scatter off each other. So these are like two electrons just bouncing off each other. Okay. For example, right, what we're going to find in chapter 5, so I'm trying to remember these chapter 5 numbers, if we actually smash an electron and a positron together, right, so this is an incoming particle, this is an incoming antiparticle, so in the Feynman diagram it shows a outgoing arrow. Okay, let's say it annihilates and then it turns into a mu plus and a mu minus. Okay, so it's outgoing, okay, right? That matrix element, right? This thing here, right? It's gonna be, well, we're gonna put a I in front of everything so that whenever you do the complex conjugate of it, you always get the negative I, so that the magnitude always comes out to be a positive number. Okay, and it's gonna turn out to be this complicated stuff that don't copy this down. Okay, But, okay, but what we're gonna see is that they're gonna be these things called U's, which is these spinners that I talked about, which is like four-dimensional, four-element vectors of wave functions. And then the V's are the anti-particle spinners, okay? And we're gonna see how these two chapters will take us to being able to calculate this IMF thing, okay? The goal is to get to something like this, okay? All right, and this is gonna take us at least 3 weeks, and we'll see if it takes a little bit longer, which is okay, okay? Because if we have a firm foundation of this, what we see is that if we try to do quantum chromodynamics, it'll be very similar, but then a lot of stuff just can't be solved because of the strong force. And then we're gonna try to, and then we're gonna apply this also to the weak force, and then we'll see how the Higgs boson actually comes out of this in about, 10 weeks or so, okay? All right, so let's start talking about the Schrodinger equation again, right? This guy always gets mentioned everywhere, okay? Right, so the Schrodinger equation tells you that, well, the time evolution of some wave function is determined by this Hamiltonian, right? Okay, right, it's just definition of a Hamiltonian, okay? So for a free particle, right, let's say for a free particle, we only care about the kinetic energy, right, which is p squared over 2m, which is basically, 1/2 mv squared at some point, if you convert that. Okay, that turns it into, let's say in spatial representation, right, some partial derivative with respect to space squared, because you have this p squared thing here, okay? So the Schrodinger equation for a free particle that we actually, play around with in chapter 2, right, is that the time derivative of the wave function is equal to the second spatial derivative of the wave function, okay? This is inherently non-relativistic, right? Because in relativity, space and time can actually swap with each other, right? Something that has a long, let's say you're trying to travel a certain distance, right? But if you're traveling at the speed of light, that space actually contracts to 0, right? And therefore, you cannot actually treat space and time differently in a relativistic theory, okay? And this is where people come up with the Klein-Gordon equation, which is the first attempt in order to figure out, can we write a relativistic version of quantum mechanics, okay? Okay, the Klein-Gordon equation comes from the Einstein energy momentum relation, E squared, P squared, M squared, right? You're just gonna have that, this will be like in your head, for the rest of your life. It's just such a useful relation, okay? So if we operatorize, okay, I made up a new word, operatorize, right? Just making these quantities into operators, okay? So we have some energy square operator operating on some wave function, some momentum square operator, right, operating on some wave function. Same thing with the mass, which is just a scalar, which is nice, okay, on your wave function also. If we convert this to, once again, now we're gonna deal with space-time, right? Not only do we have to convert to the spatial representation, but also the time representation, okay? In the space-time representation, right, these momentum turn into gradients, right? Okay. Okay. And then the energy, right, turns into time partial derivatives, okay? We plug all this stuff in here, right? Just plug this back up. Let me use a different color so that it's not black ink on black ink. Let's use red, okay? You plug this back up here, right? You plug this one in here. I mean, mass is a invariant quantity already, so we don't have to move that around, okay? The Klein-Gordon equation turns into, right, a second time derivative on the left-hand side, and then also a second spatial derivative on the right-hand side, great, okay, minus m squared, okay? And remember, we made this a little bit neater with this operator called the D'Alembert, okay, where I just call it box, okay? Remember, box is just the covariant derivative producted with the contravariant derivative product with the covariant derivative, okay? So combining these together, right? If you move this to the left-hand side, right, you pick up a negative sign, okay? What you can do is then you can write the Klein-Gordon equation as just box psi minus m equals 0, right? Very simple equation. That correctly? Okay. Wait, did I move that correctly? I think there's a plus between them, right? Because there's this minus here. Yeah. Plus. Sorry about that. Okay. So you can plug in some wave function, right? Just as always in physics, we use plane wave solutions, right? Because if we can solve the equation for one particular momentum energy wave, right? We can just add up different momentum energy waves together to get a complete solution. Okay. Okay, you plug this back in here. Oops. And you do all these second derivatives. Let's go up here. Let's not do the box version, right? That's very complicated, right? You plug this in here. Okay. What you're going to find is that, right, the energy that's going to come out of the Klein-Gordon equation has two possible solutions because of the squares in the time also, right? Right? When you're solving with a second derivative with respect to time. Okay. Okay. So you end up with some equation that's E squared equals to P squared plus M squared, which is what you expect, right? So the solution to this is that there's possible a positive energy solution and then a negative energy solution, right? Like, well, okay, whatever, right? So in special relativity, that's fine, right? People just ignore the negative energy solution, right? It's like, okay, it's non-physical, so it's just a artifact of the mathematics we're using, right? Okay. The problem is that in quantum mechanics, if you have a solution, it must be accounted for. It could, interfere, right? When you do the superpositions of states, right? All the possible wave function has to be accounted for. Otherwise, right, you don't have a complete solution to the whatever system you're trying to solve. Okay, right? Because even like minute contribution could either constructively or destructively interfere with your complete solution. Okay, people were still, not very happy about this, but okay, So one of the things that Dirac came up with to solve this negative energy situation is that he thought about, well, if we can think about our universe as just, at the zero energy, right? Let's just define the zero energy as a vacuum. Okay. Right. But, right, there's a bunch of negative energy state that's possible, right? So what happened is that if I fill all these negative energy states, I think this is what this blue diagram is supposed to be showing, right? If all this gets filled, right? So imagine if you have a bunch of particles, right? And you just have a vacuum, but it is possible for the energy for those particles to sit negative. But if you have an infinite number of particles that's just kind of sitting in this negative well, right? It fills up until it reaches zero, which is where we define vacuum of our universe to be. Okay. Imagine you have a hole in the ground, right? That's infinite, and then you fill it with infinite amount of cement. Okay, you can see why this is a little wonky, but okay, right? But now, once you fill it with like this infinite amount of cement, and then we define the top of the well, where the top of where you filled all the cement to at zero, right? Anything on top of this is the other particles that's floating around with positive energy. This should bother a lot of you guys, right? But okay, so we have to deal with this, but okay. The bigger problem, that's not the big problem actually. The bigger problem is that the Klein-Gordon equation actually have negative probability density. Okay, what the heck is probability density? Probability density, remember back in chapter 2, we talk about, let's say you have some volume, right? With some volume capital V, right? And there's some, there's some particle flowing in and some particle flowing out of these things. And then if we have some, little surface ds, right, we can calculate the probability of that particle being inside this box this sphere or not by calculating, right? How does the density, this is the density of the particles inside that box, right? Right. And it's the divergence of this current that's flowing out of your box, right? If those have to add up to 0 because, right, whatever particle flows out of your box, right, negates the amount of the number of particles inside the box, right? So I think the example I tried to give when we were talking about this, like right now we have 6 people in this room, right? Sorry, those of you on Zoom. There's 6, trust me, there's 6 people in this room, maybe, possibly. Okay, right? Okay. If, right, there's a current of 1 student per minute flowing out of this room, the change in density, right? This is actually easier to understand if you don't, you know, put this both on the left-hand side, right? Equals to negative d rho dt, right? Whatever flow of students coming out of this room is equal to the negative of the change in density of students in this room, right? Hopefully. So this is known as a continuity equation, right? Hopefully that's, you may see this in classical mechanics and other topics also. Okay, very important to just have that always, just like E squared, P squared, M squared, knowing that stuff flowing out of the room negatively impacts the density of the stuff inside of it, right? Okay. We're not going to go through all the mathematics because Thompson skipped it, but yeah, I'm not going to make you guys do it in homework either, because since the Klein-Gordon equation is not actually what we're gonna be doing later anyway. Okay. So in order to figure out what these J's and rho's are, okay, what we can do is we do a little bit of mathematics where we take psi star times this equation up here, up here, 4.1, right? The Klein-Gordon equation. Okay. Right. And then subtract it with psi times the Klein-Gordon equation with the complex conjugate version of it. You just make the, wherever you see I, you make it negative I instead. Okay. If you were to do that, so if it were a few steps of algebra, okay, you're going to see that there's going to be some time derivative, time of some stuff, and then a gradient, sorry, the divergence of some stuff. Okay. Okay. And why do we want to do this? Okay. Note that, right, this time derivative is exactly what's up here in the continuity equation, right? This divergence is exactly what's up here in the continuity equation. So by just comparing these two equations, that, right, what is this? All right, I'm going to highlight this in green. You guys tell me what that is. Okay. Right. Okay. What is that in terms of what's in the continuity equation? Let's have someone on Zoom at first. You can do it on the chat, or you can just unmute and say something. What's the stuff in green going to be equal to inside the continuity equation? This Friday.
That like the commutator of those?
Commutators between operators. So these are just right? I mean, the time derivative is an operator, but yeah, but we're not doing two operators. So we have a time derivative here times something, but we're taking a time derivative of something, right? Is there anything up in the continuity equation that's doing the time derivative of something?
Is it the expectation value?
The expectation value is going to be where you're doing this stuff, right? Psi x psi, and then integrating dx or something like that. So that's not quite there. We're just comparing these two equations. So the answer is up here somewhere, okay? I think there are 1, 2, 3. There are 3 variables in that equation. Okay, let's have someone on Zoom real quick if someone wants to try it again on Zoom. Okay. maybe what I'm gonna do is I'm gonna write these two equations next to each other and even make it a little bit more clear. Okay, this is a trick that, that's very useful. Okay, that's why I want to kind of run this a little bit. Okay, so I'm just going to copy down this equation over here. The divergence of the current equals to negative of the change in density of the probability, change in the probability density. Okay, the thing in the green here, what does it correspond to the thing on the right here? Which variable?
I mean, that just relates to rho. Or
Right,
Yes, the
that's
density.
exactly rho. Well, negative of rho, right? Basically, right? Okay. So rho, right? We're going to put a little I in front. Okay. And in fact, I think what Thompson did is he made the current negative as opposed to the rho negative, but these can swap back and forth between them. Put a little I in front of it. So the rho is exactly what's highlighted in green here. And we're not going to dwell on the current part, right? The current part, right? So it's exactly going to be what's you're taking the divergence of with a negative sign. Okay, so one of them has to have a negative sign, so we just pick the current to that. Okay. If you were to do this partial derivative with respect to time, right? Remember the wave function up here, all the way up here. You have to go all the way up here, right? If you do a partial derivative with respect to time with the wave function, you're gonna pop down an energy, right? Okay, times that wave function. Okay. Well, with the probability density function, right? When you do this time derivative, you're gonna pop down an energy. So this is gonna be proportional. So this whole thing is gonna be proportional to energy. Okay, so therefore, the probability density, we don't have to deal with this normalization factor. It's going to be proportional to the energy of the particle. But when the energy is negative, what the hell does that mean? So you have negative probabilities of stuff to exist. Okay, it's as if there's some holes in like probability of having students in this room. Okay, so that's the problem with the Klein-Gordon equation. Okay, now we can't really like get out. Okay. Okay.
I think I'm sure you already just said it, but I missed it. Where do we get the I from again?
The I is just placed in so that when you take the complex conjugate square of it, you get a real value.
Oh, okay.
Yeah, they just added it. Because I can multiply both sides of this equation by I. We'll do the same thing.
So, oh,
Yeah, whatever I define to be rho, I have the same factor in I and J, it'll be the same. Yeah. Okay, any questions and concern on in person or on Zoom? Okay. So I didn't want to like write anything about this, but if Alex is around. So there is this thing called the scalar electrodynamics, which does use the Klein-Gordon equation. So if you want to comment on that, you can, because I don't want to say something and it's probably going to be wrong because I don't actually use it.
It's not something I've thought about, so I don't, nothing to add.
Okay, right, good. Because it is interesting because it describes the dynamics of a scalar, which we now have one of, right? So the Higgs boson. Okay. I wonder if people use that to describe the Higgs boson's dynamics. Okay. At least to itself, right? The self-coupling of the Higgs bosons. Okay, so this is where we're gonna come up with the Dirac equation. And this is where things get a little bit more complicated mathematically because we're gonna have to keep track of matrices instead of dealing with scalar wave functions, okay? Okay. So in order to describe electrons and photons, right? So far, we haven't like say anything about, oh, so a lot of you guys, in like high school chemistry, you might have learned, oh, you know, the electron has a spin 1/2, right? And it could be spin up, spin down, something like that, right? When people describe nucleus and stuff like that, right? In case you don't know, the photon has a spin of 1, okay? So it could be spin up 1, spin 0, or spin down -1 in the assignment value, okay? So, and this is what's gonna just come out naturally without me telling you this from the Dirac equation. It has to be this way if it obeys, if electrodynamics obeys the Dirac equation. Okay, so what we're gonna do with the Dirac equation is that we're gonna change the Hamiltonian in the Schrodinger equation from a second order equation, right? Well, a first, so let me just write this down. It's always good to write down the Schrodinger equation, okay? At least in the spatial representation, right? So, yeah, whatever the Hamiltonian is on the wave function, okay? And remember these h, right, used to be p squared over 2m's, which turns into partial by partial x squares, right? It's probably 1 over 2m in front of here. Okay. So this is inherently a second order spatial, second order differential equation. What we're gonna do is we're gonna force this to be first order still, okay? So this one is second order. Okay, we're gonna force it to be first order instead, okay? And some funky math gonna come out, okay? And we're gonna have to deal with it, okay? This is known as the Dirac Hamiltonian operator, okay? HD, okay, not high definition, okay? And so it's gonna have some matrices. We're gonna call this first one alpha, and it's gonna be dot producted with the momentum operator, okay? Okay. This is actually a vector of matrices. Okay. And then this beta is a matrix also, okay? Multiplied by the mass, okay? Let's not deal with what these matrices exactly look like yet, okay? What we're gonna do is we're gonna put this Hamiltonian into the Schrodinger equation, right? Remember that the Schrodinger equation was whatever the Hamiltonian is, you put it on the right-hand side, okay? You still have this time derivative on the left-hand side, okay? And what we're gonna do is that when we do this dot product, okay? That's right. I'm missing, sorry, I think I'm missing a negative I here, yeah. Do that. No, it's just the Hamiltonian on the right-hand side. So, okay, let's not worry about where these little negative i's come from everywhere, but when we do this dot product, so this vector and matrix, right? This alpha, vector, right, has an alpha x, has an alpha y, has an alpha z to it. I guess that's where they can put these negative i's in there. Okay. Okay. When you do this dot product, right, with the momentum operator, the momentum operator in spatial representation is partial x, right, partial y, partial z, right? Okay. When you do a dot product between them, right, the x component dot multiply with each other, the y component multiply with each other, the z component multiply with each other. Okay, I figure out where the i's came from. It's from the momentum operator, of course. There. So these alphas don't need it. Okay. Okay. So when you plug the Dirac Hamiltonian into the Schrodinger equation, you get this on the right-hand side instead. Oh, it is tiring. Right. Okay. And what we're going to do is we're going to try to figure out if there's a way for us to calculate, well, what are the possible energy states for this, right? Okay, doing the same thing what we did with the Klein-Gordon equation, make sure that this equation actually works and describes through the real world. Okay. And so the next step is we're going to square it, and hopefully you can all see on Zoom, we're putting squares in parentheses, right? Because we're not really squaring it. Basically what you're doing is you're taking another I partial t on the left-hand side, and you're putting another operator, the same thing here together. So you're not doubling the wave, you're not squaring the wave function part, you're only squaring the Hamiltonian and the partial derivative part. Okay. And I'll show you this algebra right now. It's kind of nice to just see that. Okay. So, right, by squaring it, you mean, well, the left-hand side, if you put another factor of this in front, you get negative because I squared is -1. Okay, partial by partial t squared. Okay. The right-hand side is going to be a lot of what is that called? It's not foiling. It's multiplying things with multiple terms. Is that factoring is the other way, right? It's going backward. Defactoring, whatever that's called. If someone knows on Zoom what that's called, anti-factoring. Let's not use anti for that. I think defactoring, because we're going to use anti soon for something else. Okay. Anyone on Zoom knows what that? I think it's just multiplication, right? Yeah. Okay. This turns into a big mess. That's why I want to show it to you. Well, Thompson show it to you here. Okay. So this term with this term, right, gives you this first term, which is alpha x squared, and then the second derivative, the second spatial derivative of the wave function. Okay, fine. Similarly with y, similarly with z, similarly with the mass, right? So those are the square terms. Okay. But then you have all these cross terms, right? When you FOIL, remember, like a plus b times c plus d, right? You have these cross terms, not just a squared plus b squared plus c squared plus d squared, right? There's all these, a, b's and c, d and junk like that. Okay. Okay. So how do we deal with this? Okay. Right. So there's a cross term between x and y, right? And then we're going to combine, and these cross terms, since these are operators or matrices, they don't necessarily commute. So you have to write them with a different order. Okay. And then you have a partial derivative with respect to the wave function with each of the x and in this case, the x and y, and partial derivative with respect to x and y does commute. That's why you can combine them together. Okay. Similarly, with the cross term with yz, zx, right? And also with the mass, right? These mass terms, right? This gets multiplied to mass, right? There's also a bunch of these terms down here. Okay. Right. This turns into a big mess pretty quickly, right? It's 3 lines long in a textbook. That's a very, really long equation, right? Okay. What we're going to do is we're going to try to force this to obey the Einstein energy momentum relation once again, right? Remember E squared equals p squared plus mass squared. Okay. Okay. In this space-time representation, right? The E squared is the second derivative of time, right? Which is great. Check. Done. Right? Left-hand side is done. Okay. All right. But these other terms, right? You have a second derivative with respect to x. Now let's do a highlighted version of this, right? We have that. Okay. But we have something else in front of it. Okay. That means whatever alpha x square is, it has to be the identity matrix, right? The matrix equivalence to a 1. Thumbs up, thumbs down. Makes sense why we have to do that. Okay. Therefore, whatever alpha x squared is has to be the identity matrix. Okay. Similar argument when you have alpha y squared, alpha z squared. All of those also have to be the identity matrix. Okay. Right. And then the last term here, let's do, we have more colors, okay? The last term here, right? M squared, right? You have an M squared term here, right? And so beta squared also have to be the identity matrix. Wherever that happens to be. Right? So we got all of this stuff up top, but then now we have to deal with these cross terms, right? Cross terms always get you. Okay. The cross term is telling you that, well, in the Einstein energy momentum relation, there is no cross term. So therefore, this has to be 0, 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 this has to be 0. Okay. Okay, let's deal with the beta version first. Okay. Okay. Which is the ones with the beta, which is the last row. Yeah, so let me erase the purple on the non-beta version. Okay. Right. That tells you that whatever this anti-commutation relation is, okay, this has to be equal to 0. So what the hell is an anti-commutation relation? Remember, regular commutation relation is that you have some operator A and some operator B, right? That's defined as A times B minus B times A. Anti-commutation relation, it's very similar. You put a plus sign between them. Okay. Notice that there's a plus sign between these guys, right? This is an anti-commutation. So these alpha and beta matrices has to anti-commute with each other. So that's why I didn't want to use that word yet. Okay. Right, to deal with the, well, what color are we at now? Let's do green. Oh, let's go back to green. Yeah, to deal with these other green terms, right? We have the anti-commutation relations between these alpha matrices only if the matrices are not the same index, right? Because remember, right, if it's x squared, right, if both of the indices are x, it's supposed to be the identity matrix, right? And identity matrix commutes and anti-commutes with everything, right? So you don't want that. So therefore, you have to have this condition where these two indices cannot be the same as each other. Okay. Okay. And you will show, sorry, before I move on, so this anti-commutator thing is a new thing, so I just want to make sure people are okay with it. Any questions on why these conditions got apply if we had this long string equation up top and we're trying to force it to obey the energy momentum relations?
So, I get just a little confused in terms of the conditions.
Mhm.
So if we have alpha x, y, and z squareds equal to beta squared, those become I, or that's just other ways of
Alpha, X,
the
Y,
yellow, the highlighted yellow.
right, so whenever you square the alpha matrices, whenever you square the matrices with itself, right, you know, alpha X squared, Y squared, whatever it is, then it has to be the identity matrix, because in order to,
Oh,
that's the only way it can obey this still, okay? Okay, but the funkier things is these other matrices, right, where is instead of the subtraction between these matrices, we get a plus sign between the matrices, just because, right, when we foil, is it like called foiling? Whatever the four-term version of foiling is, right? Right, whenever you fold this out, you have these plus sign between them. And the only way that things don't commute with each other is if they are matrices, right? That's why these alphas and beta is forced to be matrices.
and the K and J's are just arbitrary?
K's, they're just indices, right? I could have used like I and J, whatever. Yeah, these are, so yeah, so that's a good point to bring up. So these J's, right? J can be equal to, you know, X, you know, 1, 2, 3, basically. J is 1, 2, 3, where 1 represents the X part, 2 represents the Y part, and 3 represents the Z part. Okay. That's a really good clarification. Sorry, I didn't do that. Okay. Any questions on Zoom? Okay. All right. So you will get to show this, of course, it's going to be a homework problem, okay? That these conditions above is going to be satisfied with this version of beta matrix. Let me just write that out, because I think the book doesn't like to, I think it's just trying to save space. It's a matrix of two identity matrices, okay? Meaning this beta is actually 1, 1. Since there's a negative here, -1, -1. Everywhere else is 0. Okay, so when you write a matrix like this, you have a bunch of off diagonal stuff that all are the same. You can just write a big O there. Okay. So this is a 4x4 matrix, right? Okay, and this 4 is going to come up soon in a second here. Okay. Similarly, these alphas, right? Let's do alpha X. Alpha X is the same thing as 0, sigma X, 0, where sigma X is another matrix called the these Pauli matrices, okay? I think we dealt with them in chapter 2 a little bit, just play around with them. So now they're coming back again, right? Okay. So each of these is actually a 2x2 matrix. So what we're going to do is we're going to expand this out and write it out in the full glory form. So since this is 0 and this is a 2x2 piece of it, right? There's going to be 4 zeros here, 4 zeros here right away. Those are the 0 matrices. Okay. Sigma x is 0, 1, 1, 0. And then this is also sigma x is 0, 1, 1, 0. Okay. So notice that the beta is the diagonal, right, matrix. And then sigma x is the off diagonal matrix, right? Sorry, it's not even called off diagonal. It's like diagonal the other way. I don't think there's a term for that. Okay. All right, and I'll let you guys play around with the sigma y and sigma z. Okay. And you're gonna, in the homework, you're gonna try to, you know, check that these relations actually are obeyed by these Pauli matrices. So this is these Pauli matrices is in a particular representation. This is called the Dirac Pauli representation, hence because Dirac used it, and then he was using Pauli matrices. There are other representations that could be useful for solving other systems, but we'll just stick with the Dirac Pauli representation for now. Okay. So these are 4x4, and they're also known as Hermitian matrices. Hermitian means, right, when you have a matrix, the complex conjugate, and the transpose, known as the dagger of it, is the same. Okay. So we'll have you check that too. Okay. Just make sure that these matrices are Hermitian. Okay. The problem is that, right, since you have, right, go back up here, you have these matrices acting on your wave functions. So the wave function also have to be how many components? We have a 4x4 matrix. How many components do we need in order to act on that? Yeah, you need a 4 component vector. Okay, it's 4 vectors, something's different. Okay. So therefore, whatever the wave function is, has to have 4 components to it. And now, right, this is where very confusing. So the psi that used to represent one function now represents 4 different functions as a vector, right? Even though there's no, you know, vector hat above it. Okay, so just be a little careful. Okay. Okay. Okay, these are known as Dirac spinors. Okay, and we're going to see why they're called spinning things. Okay. For example, if you want to explicitly calculate beta producted with psi, right? Remember, beta is this matrix up here. I just copy it down here, right? Okay. And then the wave function has 4 different components to it, right? When you have beta acting on psi, right, you have to do the product. Okay, so be a little careful, right? This is kind of special, right? So the first answer here, let me just expand this out, right, is 1 times psi, right? 0 times psi 2, right? 0 times psi 3, just so we can practice doing some matrix multiplication, right? So 0 times psi 4, right? And that's why this is just psi 1, okay? It almost looks like the identity matrix because, you know, if you have just a row of a diagonal of 1s coming down, you have the identity matrix. That means, you know, whatever it acts on, it'll give you the same thing. So the only difference down here is that it's going to give you a negative of the psi of the wave function at the end for the bottom 2 components. Okay. And that's going to be fun because, right, we're going to see why that's important for us to get positive energy solutions. Okay. Sorry, positive probability solutions. Okay. And I spelled direct wrong, of course. Okay. So I think I'm going to wrap up here because my time is up anyway. So this Dirac Hamiltonian operator, right, when you plug this into the Schrodinger equation, right, you're forced to make the operators into these 4x4 matrices, which forces you to have wave function that are 4 components. Okay. And we're gonna go through the consequences of this on next Wednesday, because we have the exam on Monday. Right, so